So now we are ready to integrate with respect to our new coordinate systems, in our new coordinate systems. Before we do our first example, let's look at what the volume element looks like, the dv, in our different coordinate systems. We already know how to integrate triple integrals, find triple integrals in Cartesian coordinates, and we know that dv is dx, dy, dz, or it could be dy dx dz or dz dx dy. You've already done examples using that. In cylindrical coordinates, we remember from polar coordinates that there the dA was r dr d theta, and the z is just z, so we also have dz. So our dv is r dr d theta dz. In spherical coordinates, we get dv is equal to, well, that doesn't look like a nice row. It looks like rho squared sine phi d rho d phi d theta. And if you want to, you could think about dv in Cartesian coordinates as a little box, in cylindrical as a little piece of a cylindrical shell, and in spherical coordinates as a piece of a spherical shell. Okay, we are ready to compute our first integral. Let's look at example 1. In example 1, we are asked to find the volume of the solid region bounded between the sphere x squared plus y squared plus z squared equals 9, and above the cone z equals to the square root of x squared plus y squared. And that you can see in that figure over here. So that looks a little bit like an ice cream cone. And the waffle part of that ice cream cone is described by the equation of the cone, z equal to the square root of x squared plus y squared. And the top, the ice cream part, that looks like a little piece of a sphere, and that's described by x squared plus y squared plus z squared equals 9. Looking at this, we are asked to find the volume, and we know that we need to find the integral of that region dv. So that region W, that is the solid region in the picture. I just gave it the name W. Okay, which coordinate system should we use? We have a sphere and we have a cone, and both of those are pretty easy to describe in spherical coordinates. So we are going to use spherical coordinates. Okay, so we need to find the limits of integration, and to find the limits, we need to describe our two equations in spherical coordinates. On the one hand, we have x squared plus y squared plus z squared equal to 9. And we know that x squared plus y squared plus z squared is the same as rho squared. So we get rho squared equal to 9. And we know that we can rewrite that as rho equal to 3. So this is the equation of a sphere. The cone is z equal to the square root of x squared plus y squared. And here, if you remember, x squared plus y squared is equal to r squared. So we can rewrite that equation as z equal to the square root of r squared, which is r. But that's in cylindrical coordinates, and we want spherical coordinates. So we need to now go to our conversion equation and figure out what is z in spherical coordinates and what is r in spherical coordinates, and we find that z is rho cosine phi and r is rho sine phi. So now the question is, when is rho cosine phi equal to rho sine phi? We can cancel the rows. So now the question is, when is cosine phi equal to sine phi? So when are cosine and sine equal? Well, that is when phi is equal to pi over 4. And so that is the equation of a cone. So we can describe our region W now in terms of rho, theta, and phi. Oh, phi. I said it right, I just wrote it wrong. And to describe the entire region W, what values does rho take on? Well, rho can be anywhere between 0 and 3. So whenever you are in that cone, you are between 0 and 3 units away from the origin. So rho goes from 0 to 3. What about theta? Well, you have complete rotational symmetry around the z-axis. So theta goes all the way from 0 to 2 pi. And what about phi? Phi is the angle away from the z-axis. And so on the z-axis you're at 0, and on the cone you are at pi over 4. So this is how we can describe our 3D region W. So now we are ready to integrate. To find the volume, we wanted the integral of W dV. Now the integral of W, we need to turn that into a triple integral, and then we still have dV. dV, if you go up to the dV element in spherical coordinates, is rho squared sine phi d rho d phi d theta. And I can reorder that, and I actually will reorder it in a minute. But what are our limits of integration? Rho goes from 0 to 3. Phi goes from 0 to pi over 4. And theta goes from 0 to 2 pi. And you can see here that our integrand does not depend on theta. So we could integrate with respect to theta first. So we could deal with the theta first and rewrite it as the integral rho squared sine phi d theta d rho d phi. So then theta goes from 0 to 2 pi, rho goes from 0 to 3, phi goes from 0 to pi over 4. Changing the order of integration is quite simple because they are all constant for this example. So as I just said, our integrand right here doesn't depend on theta. So when I integrate with respect to theta, I just get 2 pi, because that is the distance from 0 to 2 pi. And then I'm left with the integral from 0 to pi over 4, the integral from 0 to 3, rho squared sine phi d rho d phi. Okay, I need a little bit more space. Next, we integrate with respect to rho. So the antiderivative of rho squared is rho cubed over 3 sine phi, and then we are going from, rho goes from 0 to 3, and then we still have d phi to deal with later. So I'm doing this part in the middle right now, and when I plug those limits in, I get 2 pi, still have the integral from 0 to pi over 4 with respect to phi, and I get 3 cubed over 3 sine phi. And when I plug in 0, I get 0, so I don't have to deal with that. And then I have d phi. I can clean this up a little bit. So 3 cubed over 3, that's 3 squared, that's 6. So I have, oh, that's 9, sorry. I have 18 pi. And then the integral from 0 to pi over 4 sine phi d phi. Oops. Okay, almost done. Now we just need to integrate with respect to phi, and the antiderivative of sine phi is minus cosine phi. My limits go from 0 to pi over 4, and so when I plug those in, I get 18 pi times minus the cosine of pi over 4 plus the cosine of 0. And looking at, if you remember the unit circle or plug this into your calculator, you get 18 pi times minus the square root of 2 over 2 plus 1. And you can simplify that a little bit as 9 pi times 2 minus the square root of 2. So this is our final answer. This is our volume. The units, if you go back to, they didn't tell us any units, but their volume. So if in our original problem we had centimeters, then the volume would be centimeters cubed.